Right now, there are roughly 1.386 billion cubic kilometers of water on Earth. That number is so large it's essentially meaningless, until you realize it represents every ocean, every river, every cloud, every drop of blood flowing through every living creature on this planet. But here is the question almost no one stops to ask. Where did all of it come from? And perhaps more urgently, where is it going? By the year 2100, an estimated 10 to 11 billion people will share this planet. The water supply will be largely the same as it is today. What changes is almost everything else. 4.6 billion years ago, the solar system did not exist. In its place was a vast cloud of gas, dust, and ice, rotating slowly, cooling gradually. Gravity did what gravity always does. It pulled everything inward. The center became the sun. What remained spiraled into planets. Earth formed in what scientists call the habitable zone. Not too hot, not too cold. But the early Earth was nothing like what it is today. It was a hellscape of molten rock, violent impacts, and temperatures that would instantly vaporize any molecule of water that dared to exist. So where did the oceans come from? The first theory, and the one with the most evidence, is asteroid delivery. During a period called the Late Heavy Bombardment, roughly 3.8 to 4.1 billion years ago, Earth was continuously struck by asteroids and comets. Many of these were carbonaceous chondrites, rocky bodies rich in hydrated minerals. When they slammed into the early Earth, they released water. The isotopic ratio of hydrogen found in Earth's oceans closely matches that of C-type asteroids, a chemical fingerprint scientists can still read today. The second theory is newer and perhaps more surprising: solar wind. Research published in 2021 proposed that hydrogen ions carried by the solar wind reacted with oxygen locked inside rock grains on incoming asteroids, producing water molecules before those asteroids even reached Earth. The most current scientific consensus suggests both mechanisms contributed. Earth's water is, in a very literal sense, a gift from the outer solar system, delivered over hundreds of millions of years of bombardment. There is a third source. As the young Earth's interior cooled, volcanic activity drove water vapor out from deep within the mantle, a process called outgassing. This water accumulated in the atmosphere, eventually condensed, and fell as rain for thousands of years. The result was the first ocean. Scientists estimate this occurred approximately 4.4 billion years ago, just 150 million years after Earth formed. Those ancient water molecules have been cycling ever since. The water being consumed somewhere on Earth right now may have once been part of a Cretaceous sea, a glacial ice sheet, or the body of a dinosaur. Of all the water that exists on Earth, 97.5% is saltwater. The remaining 2.5% is freshwater, and of that, approximately 68.7% is locked inside glaciers and ice sheets. The water available for human use, in rivers, lakes, shallow aquifers, represents less than 0.01% of all water on Earth. Put differently, if Earth's total water supply were compressed into a single 100-liter barrel, the water available for human consumption would occupy less than 1 teaspoon. Despite this, the global average person uses approximately 1,000 cubic meters of water per year, far more than most people realize, because the vast majority is embedded in food production and industrial processes they never see. Water stress is not a future problem. It is a present one. As of the mid-2020s, roughly 2 billion people already lack access to safely managed drinking water. In the American Southwest, Lake Mead, the largest reservoir in the United States, reached historic lows. India's agricultural heartland is drawing groundwater faster than aquifers can replenish. In the Middle East and North Africa, entire nations are effectively running out of renewable freshwater. These are not isolated crises. They are early signals of a structural imbalance between human demand and planetary supply. The water cycle does not simply deliver less water as the planet warms. It delivers the wrong water, in the wrong place, at the wrong time. Warmer air holds more moisture. That means when storms occur, they release more water at once, causing flooding. But it also means longer dry periods between those events. The areas that are already wet tend to get wetter. The areas already dry tend to get drier. The Himalayan glaciers, which feed the drinking water of over 1 billion people across South and Southeast Asia, are projected to lose between 40 and 70% of their volume by 2100 under current emission trajectories. The rivers they feed, the Ganges, the Indus, the Yangtze, will experience initial flooding followed by long-term reduction. Perhaps the least discussed and most dangerous aspect of the water crisis is what is happening underground. Aquifers took thousands of years to fill. In many of the world's most productive agricultural regions, the Central Valley of California, the Great Plains, the North China Plain, northern India, they are being depleted in decades. When an aquifer is gone, it does not refill on any human timescale. The agricultural systems built on that water disappear with it. By 2100, multiple breadbaskets of the world could face permanent groundwater exhaustion. Water does not respect national borders. The Nile flows through 11 countries, the Mekong through 6. The Indus is shared between India and Pakistan, two nuclear-armed states with a contested history. As water becomes scarcer, the political pressure around shared water sources intensifies. Several analysts and institutions have identified water scarcity as a significant driver of regional instability and migration over the coming century. The nations best positioned for 2100 are those with either large renewable water supplies, significant desalination infrastructure, or advanced water recycling systems, and the political stability to maintain them. The situation is serious. It is not hopeless. Desalination technology has advanced dramatically. Reverse osmosis, once prohibitively expensive, has dropped in cost by over 80% in 3 decades. Countries like Israel, Saudi Arabia, and Singapore already meet significant portions of their freshwater needs through desalination and water recycling. Atmospheric water generation, extracting moisture directly from air, remains limited in scale, but shows potential in coastal and tropical regions. Precision agriculture, using sensors and AI to deliver exact amounts of water where needed, is already reducing agricultural consumption in test regions by 30 to 50%. The trajectory from here to 2100 is not fixed. It will be determined by policy, investment, and the decisions of governments and individuals over the next 2 to 3 decades. Water arrived on this planet from the cold edges of the solar system, delivered by billions of years of cosmic collision. It built every ocean. It enabled every life form. It carved the Grand Canyon, filled the Amazon basin, and sustains every city on Earth at this moment. The same water molecules exist today as did 4 billion years ago. They have not increased. They cannot be created. They can only be managed or mismanaged. What happens to water by 2100 is ultimately a question about what kind of civilization we choose to be.